3, 4. Okay. And this is not on mute, right? Let's see. Okay. All right, we're going to continue branch handling and branch prediction today. It's my intent to finish it today so that we can go on with precise exceptions and state maintenance in the next lecture. Okay? This should be fun. But before that, I have a bunch of announcements. I don't have office hours today. I'll be traveling. There's a review session and recitation on Friday, so please attend. We've had a lot of lectures. This is the 10th lecture. I think this is the 3rd week of classes, right? 3rd or 4th, maybe. But any questions you may have, bring to the review session and the recitation. And this, think of this as a halfway review session for the midterm exam, which will be around lecture 17 or 18, I think. But unless there are dynamic events that disrupt the flow, like extreme snow or something, which doesn't seem to be happening. So please come up with bring questions and problems. Anything that you have, we'll cover them in the review session on Friday. Yes?
Is that at the lab session?
No, this is at the lecture session. So this is during lecture. Maybe I should do that.
Oh, okay.
Yeah, lab sessions are always recitations, but this time we won't have a lecture. We'll have a recitation. Yes.
Where are the homework grades on Blackboard, or are they somewhere else?
Homeworks, grades. Yeah, they should be on Blackboard. If they're not yet, they will be on Blackboard.
And the details, grades, and comments are all in your hand in their grade. So if you check your hand in your Twitter because our grades are tagged, and that'll be like my comment for all your answers.
Okay. Yeah, if you have any questions on homeworks and labs, ask Rachada and other kids. But these grades are posted. Actually, let me go over them very quickly. Let's see if this, since this is the first homework, if you want any feedback, definitely talk with us. For some reason, it's a bit slow. Let's see. Where is this? I guess I missed the shortcut. Yeah, let's look at the homework first because it looks better. This is the statistics for the homework. This is out of normalized to 100, right? It's out of 100%.
Yes.
So the median is 89, mean is 94. It's pretty good, I think. And this is a distribution. It's what the distribution looks like. Homeworks are mainly for your benefit. It won't affect your grade that much. But you're not here for grades anyway, right? No one cares about grades. You really want to learn this. But do the homeworks just to prepare for the exam. And as I said, homeworks are very similar to past homeworks. In fact, we have questions from past exams in homework 2, just to prepare you for the exam and so that to reinforce the concepts. Don't copy the answers from past exams. That's cheating. Do it yourself. But you can get help definitely by looking at the answers. That's fine with me, as long as you understand the concepts. I don't care if you get 100 out of the homework, because that won't affect your grade that much, unless you don't do homeworks. So I expect homework grades will be around here for most of this course. Let's go back and look at the lab grades too. So this is the first lab. Oh, it's up here. It's a little bit lower. Although median and mean are still pretty high. But the distribution looks a little bit different. So if you're actually around here, definitely talk with the TAs and try to push yourself up here. Because labs will get increasingly harder in this course. If you thought this was hard, this later labs might be harder. Yes?
Sorry, can you repeat where the lab grade is? Like what file it is?
It's in the hand-in directories, right?
Oh, the labs?
Yeah, the labs are not there yet?
I don't think
Okay, the labs are not
okay.
there yet, so
Okay.
you'll get the labs. Okay? And there may be, if you want them to be regraded, definitely talk with the TAs. For example, you may get a 0 because there may have been a mistake. Maybe your program didn't run, right? That's possible. Well, you should make it run, of course, but if it's a small mistake, that will be regraded. Yes?
And there are a few people who haven't submitted the lab. So
Okay.
if it, I think it's those who got
Okay.
0. But
Yeah, definitely see the TAs if that's the case. You should be submitting the lab on time. If you don't submit, don't expect a grade, of course, right? Okay. And lab 2, hopefully you know that it's due this Friday. And don't forget the extra credit. We started the extra credit. That's good. There's some for starting. Hopefully you'll finish it. And one suggestion, be frugal with your late days as much as possible. You may need them later on during the semester, because you have other classes too. Maybe you shouldn't, but since you're taking this course. But you'll have other classes, and things will get a lot more hectic later on during the semester. It's just a suggestion early on. I know you know this maybe, but it's good to think about. Plan ahead. Yes?
For the other labs, will there also be like similar extra credit, or is this like extra credit disproportionately more?
No, there will be similar extra credits.
Okay.
Maybe even easier extra credit. For example, in Lab 3, which is available online, which is due February 21st, so you can get started right now if you wish. The extra credit will be, there will be a competition, and we'd like you to optimize your design such that you get the best performance. And best performance means best execution time, not best IPC, not best clock cycle time. Best execution time overall on a program that we will run. So the top people who win that competition will get extra credit. Yes?
Do we know what program you're going to run?
I don't think you do, so you'll have to design it for yourself. Maybe we'll give you some test cases, but we'll run a bunch of battery of tests.
Wait, so you're asking us to design for something that we don't know what?
That's right. So we'll give you a battery of tests, but it won't be exactly. It will be a subset of what we will test your design on. Just like the processor design, right?
You don't really know what you're running.
Yeah, anybody designs processors today uses today's workloads, but you don't know what the workload will be a couple of years from now, right? So that's fair. Okay, and homework 2 is due next Wednesday, so don't forget that. Okay, I think I've harped on this a lot. Today we'll cover a lot of what's covered in McFarlane's paper. And please read this paper. This will give you a good idea of what branch predictors are like. And I think I'll flash a figure from this paper too. And this is for the next lecture, for Monday. I'd recommend you to read this paper. You'll understand the lecture much better. So okay, let's start with the lecture material. We were looking at more sophisticated branch direction prediction, right? And we've covered a bunch of stuff. We've covered static prediction mechanisms, and we've seen that the downside of this is they don't adapt to dynamic behavior of a branch, right? Because you have one prediction for the branch, and if the branch changes behavior, you cannot adapt to it. And then we looked at dynamic prediction mechanisms that adapt to this dynamic behavior of the branch. Last time prediction with single bit, we looked at that. We looked at the problem with it, which is it changes its mind too quickly, right? With one differing outcome from the past, it changes its mind and changes the prediction. So we added hysteresis to it using 2-bit counter-based prediction. And then we stopped here. We didn't talk about 2-level prediction. Well, I wanted to say, basically, we actually did this analysis. Why do we want better prediction mechanisms if we're already getting 92% prediction accuracy with 2-bit counter-based prediction? 92% is on average. If you read the paper, you'll see very high prediction accuracy, even with 2-bit counter-based prediction. But some applications see 70% branch prediction accuracy. So why do we want this? Basically, we went through this exercise. I'm not going to go through this again. But basically, the takeaway is, even with 95% accuracy, if you have a reasonably deep pipeline and a reasonably wide pipeline, you're basically wasting half of the work you're doing in the fetch engine. And that's 95% accuracy. Imagine what this would be with 70% accuracy. That could be a good homework question or exam question, right? You could just answer right away. So it'd be terrible, right? With 70% accuracy, you'd be fetching many, many more instructions than you actually need to fetch. Okay, so can we do better? This was the question that I asked at the very end. We looked at last time and 2-bit counter predictors, and they exploit only last time predictability for a given branch. Basically, the last time I executed this branch, where did it go? With a single-bit counter, it's just the last time, right? With 2-bit counters, it's really last n times, right? Actually, n is 2 kind of, right? Because you're biased in 2 directions. Strongly taken, weakly taken, strongly not taken, weakly not taken. With the 3-bit counter, you can actually have more history, but then you can adapt less quickly. So people have observed 2 things that have actually been implemented in today's processors, and I'll tie back to some of today's processors later on. The first realization is that this one looks at only the history of this particular branch, right? But a branch's outcome actually can be correlated with other branches' outcomes that have been executed in the past. And if you take this into account, you can do a much better prediction. This is a nice idea that could be applicable for other things also, maybe values, for example. Remember we talked about value prediction. But we'll look at it in the context of branch prediction, and we'll look at why it makes sense to do this. This is called global branch correlation. Basically, different branches are correlated with each other in terms of their outcomes. The second realization is a branch's outcome can be correlated with past outcomes of itself, of the same static branch, because the branch keeps getting executed over and over, right? And if you look at the last 16 times the branch is executed, maybe you can predict what will happen to this branch the 17th time it's executed. Kind of last time predictors exploit this a little bit, but not exactly in the way we will exploit this. This is called local branch correlation. A branch's outcome is correlated with itself. Does that make sense? So these are fundamental concepts that could be applicable to other things. Before I go into the detail of branch prediction, let me give you why I'm teaching this, because you could actually apply these to other behavior. For example, people have found that a load's hit-miss behavior could be correlated with other loads that have been executed. If you've seen a lot of cache misses recently, maybe it's a good indicator that you'll get some more cache misses. Maybe because your working set is changing, right? You were working on some data that was nice in the cache, and now you're getting some cache misses. Maybe you started working on some other data. Some other piece of data. So it's kind of like global load miss correlation, right? People have also realized that a load's behavior is correlated with itself, a load's hit-miss behavior in the cache. If a load always gets cache misses, it's likely that it's going to get cache misses in the future also. Maybe it's because it doesn't have any locality, right? If a load is always getting cache hits, it may be likely that it's going to get cache hits in the future again. Maybe because it's streaming through an array, right? We discussed this before. Does that make sense? So these concepts are more general than branches, but I'll talk about them in the context of branches. But these are good building blocks if you want to, for example, design a predictor for something, for some event in the future. It could be load miss, load hit. It's good to think about these. It's also good to think out of the box and maybe make a realization tree. But that's for you to think about in the future. Let's talk about these first. Are these clear conceptually? These are beautiful realizations, right? Okay, so let's talk about global branch correlation first. Basically, the idea is recently executed branch outcomes in the execution path of a program is correlated with, are correlated with the outcome of the next branch. Let me give you some insight into why this could be the case. Let's take a look at these two branches. Basically, you're testing some condition 1, doing something based on that. And later, you're testing if condition 1 and condition 2 hold, you're doing something else. These are two different branches, right? Well, obviously, there's some correlation because they're testing the same condition, partially. If the first branch is not taken, the second is definitely not taken. So if you had a bit indicating the first branch is not taken, then you could predict the next branch, right? It's beautiful. Let's take a look at another example. And these are examples from real programs, actually. This is from a paper by Mark Evers. I think it's called An Analysis of Correlation and Predictability, What Makes Two-Level Branch Predictors Work. It was published in Micro 1998. And these are examples from real applications. You can imagine that writing things like this, right? Basically here, the first branch is testing condition 1 and setting A equals 2 if condition 1 is true. And the second branch later on is testing if A is equal to 0. Obviously, if this branch is taken, this is not going to be taken, right? Because there's some data flow that has changed. The value of A is determined by this branch, which is tested by this branch. Let's take a look at another example. This is actually a more complicated one that looks at multiple branches, more than 2. In this case, branch Y is testing condition 1, doing something after that. Branch D is testing condition 2, doing something after that. And later, the programmer decided to test both condition 1 and condition 2. And that is what branch X does, and you do something based on that. Obviously, there's a correlation between this branch and these two branches, right? If Y and Z are both taken, then X is also taken. If Y or Z is not taken, then X is also not taken. Beautiful. So now how do you build a predictor that can capture this correlation in a simple way? And that's the idea of, well, I'm getting ahead of myself, but that's the idea of global branch predictor, which we will see. But to show you that this is actually from a real program, this was a program that was in Standard Performance Evaluation Corporation's benchmark suite. This is the benchmark suite that is used to benchmark processors for their CPU performance. And people have marketed their processors for a long time with their spec numbers. Spec number means how fast do you execute this suite of programs, which included this one in 1992. These are still used, less so today, because there are a lot of other benchmark suites that we have today, more data-intensive workloads. But these were the benchmark suites of the time to test single processor performance. And this was actually a tough nut for many processor manufacturers because of this loop, mainly. This is an optimization program. This is a VLSI design optimization program. But basically, it's very similar to this construct. You test if A is equal to 2, then you set A equal to 0, BB is equal to 2, then you set BB equal to 0, and then you test if A is not equal to BB. Obviously, this branch is correlated with these two branches, right? And you can imagine writing code like this. And it was very difficult for many processors that had bimodal or 2-bit counter branch prediction to predict this branch. And this branch was executed many times, so the prediction accuracy on this program was around 70 to 80%. And later I'll show you data on this program that global branch correlation, predictors capturing global branch correlation can actually improve the prediction accuracy to about 90 to 95% on this program. That's a huge improvement based on numbers. But hopefully you now see why this may make sense to look at other branches' outcomes when you're predicting this branch. When you're predicting this branch, if you knew the outcomes of these two previous branches, then you could do a much better job. So how do you capture that? The idea is simple. How do you capture that in a simple way? You can imagine many data structures to do this, right? But we need to implement this in hardware, and it needs to be very, very quick to do that because it needs to be done in one cycle. The idea is to associate branch outcomes with a global taken, not taken history of all branches. Have a register that keeps track of the history of last n branches that were executed. It basically encodes the taken, not taken behavior of those n branches. And make a prediction based on the outcome of the branch the last time the same global branch history was encountered. Does that make sense? Let's see. Basically, we're going to have a register. I'll call this the global history register. Let's say we have 4 bits in the register. This means that this is the outcome of the previous branch. It could be taken or not taken. Second previous branch. Third previous branch. And fourth previous, which is the oldest branch. And you shift the outcome of the branches, these branches, into this register. Now you have a value over here. The outcome of the last 4 branches was taken, taken, not taken, taken. And you could encode this taken as 0, well, taken as 1 with, and not taken with 0, right? Now you have this register. Now I can index a table that says, basically the last time I saw this pattern, if you will, in the global history, the next branch was taken or not taken, right? This could be a 1-bit counter or a 2-bit counter again. Does that make sense? The last time I saw this history, what happened to the branch that came right afterwards? Beautiful, very simple. This is called the global history register. This is called a pattern history table. And if this says taken, then when you see this history at the fetch engine, you predict the branch as taken. And this could be 2-bit counters again, if you want to add some hysteresis, such that whenever behavior of the next branch changes, when you see this history, you don't change the outcome. You don't change the prediction quickly, you can add 2-bit counters over here. It's the same concept. Yes?
Would you have a pattern history table for each branch, or?
That's an excellent question.
Yeah.
Yes, that adds to your complexity. You could potentially have it. Well, for each branch is very difficult, right? a subset of branches based on the program counter you could have. Pentium Pro had 4 different pattern history tables that were selected based on 2 bits from the program counter, for example. But in this example, let's assume that the pattern history table is shared by all branches. The only thing you do is take this global history, index into this pattern history table, and that location tells you whether you should predict the branch is taken or not taken. Basically, no program counter information in this case. It's purely based on global history. Now we're going to add information to that later on. Okay? And when you actually resolve the branch, when you made this prediction, right, for the branch at the fetch stage, when you resolve the branch, what happens is you index this table again with the same global history you predicted the branch with, and then increment or decrement the counter depending on the resolution of the branch. If the branch is taken, you set this to taken, or increment the counter such that it indicates a stronger taken state. If the branch is actually not taken, then you decrement the counter such that it indicates a weakly taken state. Okay? Well, I think I've already shown you this. Basically, we'd like to keep track of the global taken, not taken history of all branches in a register, global history register, or GR. Your reading calls this the GR, which is also fine, but GHR is more common today. Use the global history register to index into a table that recorded the outcome that was seen for each GHR value in the recent past. Okay? This is called the pattern history table, and it could be implemented as a table of 2-bit counters. And this is called the global history or branch predictor. Does this make sense? This is also called 2-level prediction, because it uses really 2 levels of history. Right? One level of history is this global history register, the direction of previous n branches, and the second level of history is here, right? History of the branch at that global history register value. 2 levels of history. Try to make it 3 levels. Okay, so this is what I'm showing over here. The first level is global branch history register, the direction of last n branches, and second level is the table of saturating counters for each history entry. And I think I've harped on this. Any questions? I don't want to repeat myself again. It's kind of beautiful, right? You don't even use any program counter information here, and this works quite well. You can read do your reading, and it shows you some actually experimental results with this predictor. Works better than the 2-bit counter prediction, even without using program counter information. You use program counter information, which we will incorporate. One way could be actually having different pattern history tables for different program counters, right, as we discussed right now, which Pentium Pro did. It had 4 pattern history tables. That way you try to add some more information. Maybe for this program counter, this history leads to a different outcome, right? Make sense? But that also can reduce your accuracy too. People have found that, this is where analysis gets a little bit hard, because sometimes you don't want to do that, sometimes you want to do that, because sometimes adding more information is not useful, because different branches that have the same history can be predicted the same way. If you have different tables, you need to train those tables separately. Because for this table to be trained, you need to see different histories, right? Yes?
I guess my question, when you said multiple program counters, you meant for like multiple hardware threads?
No, for the same hardware thread. Basically, you have, let's say, 4 tables. 1, 2, 3, 4. Imagine 4 copies of this table.
Yeah.
And you use a global history register to index in parallel to all of them. And they all provide a taken, not taken prediction. And then you mux the predictions. And what you mux it with is program counter, 2 bits from the program counter.
Okay, so it's the same program counter.
Yeah, it's the same program counter,
okay.
Exactly. This way you distinguish between different branches, or different sets of branches, if you will. It's very hard to have tables as many as program counters as you have, right? That's basically infeasible to build. But this is basically what I've shown you here is Pentium Pro's branch predictor from circa 1995. It had a 4-bit history, and it had 4 pattern history tables that had 2-bit counters. And it worked very well for that. Okay. So how does this global predictor work? If you read this, read your reading, this is basically what it shows. But I'll go through this very briefly. I'd definitely like you to do that reading. This gives a very simple code example where this works. And the code example is this. I don't like it that much because this is actually very predictable patterns. But this shows what happens to the global history register, which is called GR, for each branch that you encounter in this code. Basically, this is a nested loop. The first loop iterates 100 times. The second loop iterates 3 times, right? Yes. And this shows the global history register for each iteration of this loop and any iteration of this loop. Basically, what happens is, in the steady state, when you've actually populated your predictor, this cycles through j equals 1, j equals 2, j equals 3 values. And let's take a look at the last one. When j is equal to 3, if you have 4 bits global history register, the last 4 branches you've seen would look like this, right? Basically, the last 4 branches. What are the last 4 branches? This is the previous branch, and this is the 4th previous branch. Basically, this is older, and this is younger. This is the youngest branch before this branch. And when you're testing that j equals 3, when j equals 3, and when you're testing that condition, the last branches look like you've taken, because the last 3 branches are actually these inner loops branches, right? Because you're going through j, and you actually executed it 3 times. And the 4th one is really the branch over here that tests I if I is less than 100, right? And that's very likely not taken, right?
Well, wouldn't that be
No,
taken
it is
because
taken.
you had to take the branch to get back into the next iteration of the outer loop?
Oh,
The
I
one
see.
that's not taken is the one that goes back to the inner loop. It's the final one when it is equal to 3.
Oh, that's right. Yes,
Right.
that's right.
And
Yes.
then it goes to the next one and it does take it.
But then you take it
Uh-huh.
to go to cycle around and do the outer loop again, and then you have to cycle the inner loop 3 times before you're not taking that branch, unless I'm counting the number of iterations of the inner loop wrong.
So let's see. Let's start with this one, I guess. That may be better. Okay. Yeah. When you're testing this one, what happens is the inner iterations, I guess you do it 3 times, right? Yes. The history looks like this, right? The last one for j is not taken. This is taken, right? And these are all, yeah. This is the 3rd iteration, 2nd iteration, 1st iteration, and this is the previous one, right? For I. Is that correct? Yes. Basically, let's take a look at this one. You're right. It's easier to start with this one. And the history, when you execute this branch, usually looks like this, because this iterates 100 times. Actually, it would be better if this was 1,000,000 times, maybe, or 1,000,000,000 times. And when you see this history, that branch is usually not taken, right? Basically, you have a 16-entry pattern history table, and this history maps to somewhere here. And the outcome here is usually not taken. Now, when you go around the loop, execute the next branch, you're basically executing this, right? And this branch is taken. So you shift in the value. These branches are shifted this way, 0, 1, 1, and the branch is taken. So your history looks like this when you're predicting the first iteration of this loop, right? And you index into the global history table. Well, this is time, if you will. And you index into the global history table when you're predicting the first iteration of this loop with this history, 1, 1, 0, 1. And what you find over there at steady state is this is taken, right? Or let's say 1. Because this is always taken in the first iteration. That's just the nature of the loop. Make sense? And once that's taken, what you do is you shift out the oldest bit. Once you figure out that direction, you shift out the oldest bit, 1, 0, 1, basically shift this out, and you shift in the new outcome of the branch, which is taken, because that was the branch, that was the first branch. And this is the second branch. You index into the global history register again when you're predicting the branch in the second iteration. And again, that should, at the steady state, be taken. Because second iteration. Right? So you can think of this as testing I equals 100, testing j less than 3 when j is equal to 1, testing j less than 3 when j is equal to 2. And you keep doing this. Basically, you shift out this one because this was taken, so you shift out the oldest one, and you shift in the outcome of j equals 2, which is taken. You get 0, 1, 1, 1, and that's when you predict this branch when j is actually 3. Now j is 3. You're testing j less than 3 when j is 3, and this maps into some other entry in the global history register, actually probably up here, because this is 0, 1, 1, 1. And this is not taken, right? Did I say not taken over here? This should be taken, right? Because I was confused with taken. I'll correct it right now. So this is not taken because this is the last branch, last iteration of this loop, and that's not taken. As a result, you can distinguish between these 4 different branches based on the 4 different histories they display. It's kind of beautiful. I've kind of iterated over this predictor, if you will. Now, this works nicely in this case, but you can imagine downsides to this, right? What if 2 branches saw the same history, and they map to the same entry, but they have different outcomes? In this case, it doesn't happen, but it could happen, because you may have many, many branches in the code, right? That's called an interference in the history tables, and this may actually reduce your accuracy. I'm not going to go into this in detail, but people have tried to prevent this interference a lot in designs. Using program counter information is one way of preventing that interference. Using more context information is preventing that interference, and we're going to see that actually. But people have analyzed this interference in this pattern history table such that you get much better predictions. Does that make sense? Everybody knows how a global branch predictor works? Yes. I'd encourage you to go through this example on your own, and some of the other examples that I have. It may take a while to actually see exactly how it works. Okay, so a Pentium Pro branch predictor, I've already talked to you about this. It's a 4-bit global history register, just like this. It had multiple pattern history tables of 2-bit counters, and which pattern history table to use is determined by the lower order bits of the branch address. I've already shown you here, so I'm not going to go over that again. And I've already said that interference is a problem here. So how can you improve the accuracy, predictor accuracy? And the paper you're reading introduced one predictor that was used very heavily in processors designed after that. And the idea is to add more context information to the global predictor. That enables you to distinguish which branch is being predicted. Here, if you just use this global history register, you have no information about that particular branch, no PC information. One way of adding PC information is what Pentium Pro did. But people have found there is another way of adding information, which is called the G-share predictor. Actually, I don't know the origin of the name of your paper actually puts the name. It's really sharing the information of global history register and branch PC in one register, if you will. Basically, global history register is hashed with the branch PC. If you want to add more information, one way of adding more information is hashing multiple values together. Hashing in this case is XORing. It looks like this, basically. You have the global history register, which is that, and you take the branch program counter, or some bits from the branch program counter, XOR them, and then index into the pattern history table. Now the information you use to predict the branch includes both the global history and branch program counter. It's kind of in a nice way, in a simple way. it also adds a little bit less predictability to the process, right? Now it's harder to analyze because you're XORing two values. Okay? You can read the paper, but there are advantages to this. One is more context information. If two branches that have the same history of past 4 branches take different outcomes, now you can potentially distinguish between them because they'll map to different entries in the pattern history table, assuming their addresses, the address bits you're using coming from their PCs are different. Right? And there's another advantage of this, which we will see in caching. Whenever you do this kind of hashing, you're distributing information across this table. Right? For example, think about it. If your branch history register is all ones, everything maps to here, right? But now if you XOR it with different branch PCs, you're distributing that information across the table. So you get better utilization of the PHT, pattern history table. You're reducing interference across different branches. Now interference may not always be bad, right? Sometimes you're lucky. If 2 branches have the same history, they will reinforce each other. So it could be a good interference. You're eliminating that good interference too, but you're eliminating bad interference too. So this is reducing the conflicts, if you will, in the pattern history table. 2 things that used to map to the same entry now are mapping to different entries. And we'll see this in caching also. People use this or have proposed this in caching such that you can better utilize the entries in processor caches. Okay? Or better reduce the conflict misses. Well, I'm giving you the downside. I shouldn't have maybe. This is one of the downsides. The downside is increased access latency, right? Now you have additional XOR gates. And this is actually a critical path. Well, it could be a critical path of the pipeline because what you're doing is you need to determine the next fetch address to be used in the next cycle. And next fetch logic has been a very difficult part of the pipeline to design in superscalar processors. Because you need to figure out the address of the next instruction when you're fetching multiple instructions. And you're doing branch prediction. And we'll see that, we'll come back to that, because that next fetch address mux is actually huge. Well, there are other downsides potentially also, which is maybe you're reducing accuracy, right? But usually, empirically, people have shown that accuracy increases this way because of these 2 benefits. Any questions on this? Or is this already black magic? Yes?
So all of this logic that we can do to predict branches takes time.
Yes.
So right now, like if we have a 20-stage pipeline and we correctly predict a branch, then we can save ourselves from having to flush the pipeline, etc. But the more complex our branch predictor gets, the more cycles it takes before we can even determine a PC to go to. So how does that factor into like the amount of cycles that you're going to waste either way? Because I mean, if you have a very complicated branch predictor, it's good, like you're always going to be missing out on a couple of cycles that you could have been.
That's a great question. Basically, people try to design the branch predictor such that you can predict in one cycle.
Right.
That constrains the size and the algorithms that you employ. But one approach you could do, and some processors actually employ this, is you could use a simple predictor in the first cycle to get the next fetch address, and then have a more complicated predictor that gives you a hopefully better prediction, 3 cycles. And if the simple predictor's prediction doesn't match the complex predictor's prediction, then use the complex predictor's prediction. So that's one way of getting the best of both worlds, heterogeneity, right? Use both a simple predictor and a complex predictor. Simple predictor gives you the outcome quickly. Complex predictor gives you the outcome late, but hopefully it's more accurate. And only if the simple predictor outcome is different, prediction is different from the complex predictor's prediction, then you flush the pipeline for that short amount of time and use the complex predictor's prediction. Does that make sense to you guys? Okay. But usually, people try to design the predictor such that it takes 1 cycle. People have tried to eliminate this next fetch loop, which is a critical part of the loop, in different ways, but we'll not get into that. That's one of the reasons why predicted execution is nice, right? You don't need to predict anything. Okay, but it does other downsides. Okay, let's review the two-level branch predictor. How does it look like? Remember the one-level branch predictor, we use the program counter to index the BTB, access the BTB, branch target buffer. We also index a direction predictor, which is just 2-bit counters, and this could be in the BTB. And if 2-bit counters said taken, and if we got a target hit in the BTB, we would use the next fetch address from the target address over here. Two-level looks a little bit different. We still get the target address from the BTB for the program counter, but with the global branch history register, not the G-share, I'll show you G-share next, the direction predictor is only indexed with the global branch history. That provides a prediction, taken or not taken, and if it's taken, you take the target from the BTB, and that's your next fetch address. Now G-share, which is also two-level, you get the target the same way with the program counter. But now to get the direction prediction, you XOR the global branch history with the program counter and get the direction prediction, and based on that you determine the next fetch address. And you can imagine making this more and more complicated. And existing branch predictors are much more complicated than this. Okay. That's global history. And so there's also local history beyond last time history. So let's take a look at that. Well, I guess I'll go through this very quickly just to jog your memory. Basically, a branch's outcome can be correlated with its past outcomes in addition to the outcome of the branch last time it was executed, for last 16 outcomes, let's say, of the same branch. This is called local branch correlation. And this is actually good for loops in general. If you're doing something like this, for example, actually this explains it nicely. If you read your reading, then you can sleep right now. But if the loop test, if you look at this is a loop that iterates 4 times, right? Yes. And this is nice. But if the loop test is done at the end of the body, you could do it at the beginning of the body. Basically, you execute the loop once and then test it. The corresponding branch will execute the pattern 1, 1, 1, 0 to the n times. Basically, taken, 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 not taken. And you keep repeating it, assuming there's another loop that gets you back to the beginning of that loop. And remember, that's how the programs work. Where 1 and 0 represent taken and not taken respectively, and n is the number of times the loop is executed. Clearly, if we knew the direction this branch had gone on the previous 3 executions, then we could always be able to predict the next branch direction. Right. Does that make sense? If this branch was previously 1, 1, 1, taken, 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 the next one will be not taken, because it's iterated 4 times. If previously it was 1, 1, 0, the next one will be taken, because you've gone back to the loop again. And you can imagine that, because it keeps repeating this pattern. Yes?
But if the loop is 5, then it just breaks.
Yes, exactly. That's the problem with
So
this.
you're limited to like the size.
Exactly. You're limited to the history length. Absolutely. And that has been a problem. I think I have that on the slide somewhere. So this works obviously if this is smaller than the history. If the loop iterates 1 billion times, then you're not going to capture that. But the good news is, if it iterates 1 billion times, you don't care about a misprediction perhaps, because your misprediction rate is 1 out of 1 billion. So you really want to capture these things that are iterating few times, because your misprediction rate, remember the n minus 1 divided by n, that's the misprediction rate with a 2-bit counter prediction for these loops. This is from the last lecture. That becomes high if n is small. Okay, so how do you capture that? Well, it's the same idea. Instead of having a global history register, have a per branch history register. That's local to that branch. That keeps the outcome of the last n executions of that branch. And associate the predicted outcome of the branch with the taken, not taken history of the same branch. And make a prediction based on the outcome of the branch the last time the same local branch history was encountered. Basically, the last time you see the same local branch history, where did this branch go? Make sense? It's basically what this was saying. The last time you saw 1, 1, 1, the branch went 0 the next time. Okay. This is called the local history, or local history branch predictor. Again, it uses 2 levels of history. One is the per branch history register instead of the global history register. and the history of that branch at that history register value, which is a taken, not taken behavior. Again, that could be 2-bit counters, right? Because you may not want to change your belief very quickly if the outcome changes for that particular local branches. And this is what it looks like. Well, let's see. What do I need to say over here? In the first level, you have a set of local history registers per branch. These are per branch. Well, which means that you need to have separate tables, probably, right? Does that make sense? And then you select the history register based on the program counter of the branch. The second level is a table of saturating counters for each history entry. Again, this could be per branch, right? In the best implementation, this is actually per branch. But as we will see, alpha 21 to 64 didn't do it per branch. That's where things get a little bit fuzzy, because you have a lot of interference between different branches. But basically, ideally, what you would like is for each branch you have a local history register table. This is for one branch, and a pattern history table for that branch. Now this is very costly, so when people build these things, they try to share as much as possible across different branches. Then you get into interference issues because different branches map to the same entries, and maybe you don't get as good prediction behavior. But the second level is a table of saturating counters for each history entry, very similar to what I've shown you over here, except the history entry is now per branch. Make sense? Okay, that's the direction the branch took the last time the same history was seen. So this is, keep this in mind, maybe I should have written on this on the slide, but this shows for one branch. What this really looks like for n branches is something like this. I guess I'll draw it over here. Because you need history, you need to distinguish different histories for each branch, right? This is local history register table. And let's say you have 1,024 of these. Now you see the problem, right? And you take the program counter, take 10 bits out of it, and what you do is in 1,024 way mux. That gives you the history for that branch, and you use that. You can do this in a smarter way once you have that history, but I'll do it in the dumb way, which means you index 1,024 tables. And then you use the same program counter to pick the table for that branch. Okay. Does that make sense? Basically, you have, at least for those 1,024 sets of branches, you have a different local history table and a different pattern history table for that particular local history. Make sense? That's the per branch table, yes?
Why is it a table? Why are they like tables, not just an entry?
It cannot be an entry because what you get over here is a history length, right?
For that branch, right?
Yeah, for that branch. Basically, this is, let's say this is 10 bits, which means that you can have 2 to the 10 different outcomes for this register, which means this needs to be a 2 to the 10 entries, right?
Yeah, I mean the first level. Why is that like layers of tables? Why is not just a table?
Oh, I see. It could be a table, yeah. It could be a table. That's right. It could be a table.
Well, muxing from 1,000 tables is the same thing as having a really
That's
even
right.
longer table.
Really large
because you're
table.
just muxing out of each of those tables individually anyway.
That's right. Exactly. Yeah. It could be that way too. You're right. Basically, you could in the implementation that you will see you have one table for this, one table for this, and we'll take a look at that. Okay. Okay. Basically, this is what it looks like. This is actually one example, right? And I very simplified a lot. Any questions? Okay. Well, I guess what I'll harp on is which directions earlier instances of this branch went. That's what is added over here. Okay. So now you have the local and global history, both of them. at the same time. Is this enough? I'll ask again. And the answer is it depends, probably, right? It depends on what you're trying to do. But if your goal is to actually feed a pipeline that's very wide and very deep, again, this is not enough. This gets you around 98%, maybe, if you're lucky, 97%. So people have developed the idea of hybrid branch predictors, which is actually one of the key contributions of the paper that I've assigned to you. And the idea is simple again. Whenever you have two things that are good at different aspects of prediction, why don't you combine them and pick the best one? Use more than one type of predictor or multiple algorithms and select the best prediction. That's the idea of hybrid branch prediction. And you could have hybrids of all of these different algorithms that we've discussed. You could have a hybrid of 2-bit counters and a global predictor. A global predictor and a local predictor. Because these provide different predictability, actually. Well, why? For example, you can ask 2-bit counters. It's now not that interesting, right? Given that we've seen local and global branch history correlation. Well, there's an advantage to this also. What could it be? Basically, you use a program counter to predict, to index into a table of 2-bit counters.
Simple.
It's simple, yes.
It has like both a strong and the weak predictions, so maybe the weak one you can override with the strong one.
That's right, yeah, maybe. So what you're saying is basically maybe this gives you a strong prediction and this gives you a weak prediction. And maybe you pick the strong one. That's actually a one selection mechanism, potentially. Maybe this gives you a better prediction, that's right. Why could that be? There's one reason for that. Actually, there could be multiple reasons, but one reason is this is very easy to train, right? You see this program counter, I don't know, let's say 4 times, then it's trained, right? Because 2 bits, you just need 4 outcomes. Actually, you need 2 outcomes to get to a state. It's very easy to train. Assuming that the branch is predictable just based on the program counter, you don't care about the history, then you're done, right? Whereas if you go through the history-based predictor, it takes longer to train because a 4-bit history maps to 16 different entries, right? It takes a while to train all of those 2-bit counters. So this warms up faster, if you will. It captures the program behavior faster, assuming the program behavior is predictable just using that information. Does that make sense? The more information you add, the slower the predictor gets trained. Let's say you have a 16-bit history. Well, that's a lot of different potential history register values, right? It takes a while. So that's this one. Basically, what you can do is you can use the faster warm-up predictor, 2-bit counters, until the slower warm-up predictor warms up. Then the key question is how do you figure out the predictor is warmed up, right? Well, that may be another threshold. But the bigger advantage is you get better accuracy because different predictors are better for different branches. One thing that we will look at later on is a lot of the branches are just biased. For example, a loop branch that's iterating 1 billion times. You really don't want to use a global predictor for that, right? Because that branch is going to be taken most of the time, and 2-bit counters is perhaps enough. And you may not even want to allocate an entry in your global predictor if you could potentially do that. You may not even want to update your global predictor with that branch because you know that it's easy to predict as taken. Does that make sense? Okay. Well, I should have asked you maybe, but now we're adding more and more, right? You have longer access latency. Somehow you need to have 2 predictors and choose between them, which means another mux. And a controller for that mux. How do you decide which predictor to choose? It's called a meta predictor or selector. Which predictor do you trust more? And you mentioned the mechanism to choose. Pick the predictor that has strongly taken, or that has a strong outcome, if you will. And people have suggested that as a meta predictor. You could do that. What if both of them have strong outcomes? Now you still need a meta selector, meta predictor.
You can keep a history for that.
Exactly. Exactly. The idea is you can keep a history of which predictor is doing better. Now you got the hang of it. And that's right. People have found out that and the paper you're reading, maybe you got it from the paper. Did you read the paper?
No.
You know, this is a trick question because either answer you give would be bad for you. Just kidding. But yes, that's a good idea if you haven't read the paper. Basically, some different predictors are good for different branches, and you could figure out based on history. And different predictors could be good for the same branch at different times. And people have found that too. Because branches, again, change behavior. That's the beauty of this dynamic prediction. You can adapt to what's happening. Dynamic. Well, I'll give you a real implementation from the fastest processor of its time, Alpha 21-264, which you should be reading soon. But this is their predictor. They called it the tournament predictor. And this is actually really implemented. Existing processors are very similar, except they add more stuff. Basically, what they did was, let's start with the global predictor over here. They had a global predictor with 12 bits of history. That's a lot of branches, right? And that's the global history register, and that's the pattern history table, 2-bit counters, 4,096 of them. That gave a global prediction. And this is the local predictor. You index with the program counter. You have one table, and you have another table over here. And local history table, the program counter, you take 10 bits from the program counter and index it. That's why this has 1,024 entries. And you have a 10-bit local history register for that branch. And you use 10 bits to index into the pattern history tables. In that case, you have, again, 1,024 of them, but they use 3 bits because they found out that 3 bits work better for hysteresis. Interesting, right? You don't change your outcome quickly. And that gave a local prediction. And see the size of the tables, even though they're drawn the same. This is much smaller, right? This is 4,096 entries. This is 1,024 entries. Why? Because there's an indirection here, right? You actually access 2 tables over here. So the tables are sized such that they provide their prediction at approximately the same time. And of course, you need to choose between them, right? Do you pick the local predictor, or do you pick the global predictor for that branch? Well, how do you do that? They have a choice predictor. This is the meta predictor that I mentioned, selector. And there's also 4,096 entries, and they use the global history, purely global history, no branch program counter, to pick the final prediction. And this performs pretty well. Alpha had a pretty good branch prediction accuracy, 21-64. So what you just learned actually is not useless. If you go and design branch predictors later on, you'll need to do much more than this today. Okay, so for alpha, I'll cover some of the things that are much more. Minimum branch penalty was 7 cycles. Branches were resolved 7 cycles. This was a deep pipeline for its time. Remember, this is circa 1996. The paper is written in 1999. Typical branch penalty was about 11 plus cycles, according to their reference manual, because it has out-of-order execution and branches are resolved based on data dependencies. And they actually store the target addresses in the iCache. And they reset the predictor tables on a context switch, such that you start out fresh for a different thread. So these are some of the issues. There are a lot of issues related to branch prediction. And this gives you some of them. So what is the accuracy? This is from the paper you're reading. And this is not the best one. This is not Alpha's predictor. Alpha's predictor is better than this, actually. But bimodal, remember, that's a table of 2-bit counters indexed by the branch address. G-share, we've discussed. Global history predictor. Global history XORed with the branch address. And bimodal / G-share is a hybrid predictor of both of them. And you have a choice predictor. And this is spec 92 benchmarks. At that time, processors were tested with these. And if you look at this, I guess there's an average here. Bimodal predictor, just 2-bit counters get you to about 91%. G-share gets you to about 94%. And the hybrid gets you to about 96% for these workloads. And some of them are very nicely predictable over here. These are more scientific applications with loops that iterate many, many times. And these are GCC, is a hardware application. It's a very irregular application. Now GCC you used, right? It's a compiler, GNU compiler. And it usually has the lowest accuracy, prediction accuracy. And you can see some anomalies. Well, maybe it's not an anomaly. Now you know why this may happen. For example, bimodal predictor performs better, 86% accuracy compared to a G-share predictor on GCs, 84%. But the hybrid one actually fixes that problem, gets the best of both worlds. And this is the one that I showed you over here, equivalent thoughts. Its prediction accuracy is about 81% with just 2-bit counters. G-share pushes it up to 94% because of global branch correlation. So you can read this paper for more. But this shows that actually these ideas work. Biased branches, I already talked about this. Many branches are biased in one direction. For example, 99% taken. If you actually use these sophisticated predictors to predict these branches, what they do is they cause pollution in the branch prediction structures. Pollution means they occupy entries in the branch prediction structures that affect other branches, but they do not provide a lot of benefit because they could be predicted much more easily. We'll see this idea of pollution in caches also. If you're storing a memory block in your cache that you're not going to reuse, that just pollutes the cache. It's occupying space, but it's being useless. Right? It's preventing from some other useful block going into the cache. It's a very similar idea. Basically, whenever you have a table, if you occupy an entry, and the entry is not beneficial, then you're polluting that table. You're basically preventing something else from using that entry. So these branches, biased branches, make the prediction of other branches difficult by causing interference in these tables, by polluting the tables and the history registers. So if you can somehow filter these out, you can do much better. And the solution people have proposed is detect such biased branches and predict them with a simpler predictor. Loop predictor is one of them, for example, you had mentioned in the last lecture. For example, if you can identify the loops and predict how many times it will iterate, you don't need to go through all of these hybrid predictors, right? You can just use that loop. Uh-oh, this doesn't look good now. And I definitely need this.